Saturation policies. When the work queue in the thread pool is full and the pool is at max size, the saturation policy kicks in. Thread pool executor provides four built-in policies. These are the standard implementations of rejected execution handler, which you can pass as constructor argument while creating thread pool executor. So let's see all these policies. First is abort policy, which is the default one. It throws rejected execution exception when queue is full and pool size is at max, and the caller must handle this exception. Discard policy, as name suggests, it silently discards the new task. Discard oldest policy discards the oldest task in the queue and then tries to submit the new task again. Note here, if you use a priority queue, this discards the highest priority element, probably not what you want. At last, we have caller runs policy. Instead of rejecting, it executes the task in the caller's thread. This acts as a throttle. The caller thread does the work, so it can't submit more tasks for a while, giving a pool a time to catch up. The caller run policy is especially powerful. In web server, if the pool is overloaded, the main thread that accepts the connection will start processing the request itself. That means it can't accept new connections. So the requests start backing up in the TCP layer. The overload pushes outward and the system degrades gracefully instead of crashing. But what if you want the submitter to block instead of making it run the task until pool thread is available? There is no built-in policy for that, but you can implement it using Semaphore. You create Semaphore with the bound equal to the pool size plus the queue capacity. And before submitting, you acquire the Semaphore, and after task finish, you release it. This limits the number of pending tasks and naturally blocks the caller when the limit is reached. This is a great technique for controlling injection rates. Let's try to implement it. Bounded executor, which limits the number of tasks submitted to an executor by using semaphore. It blocks the caller when the limit is reached, providing backpressure. So we take executor and maximum number of tasks allowed to be pending. That means task may be running or queued. So here we have submit task method where we submits a task to the executor. If the limit of pending task has been reached, the calling thread blocks until a slot becomes available. So we first acquire a permit before submitting. Acquire method gets blocked if there is no permit available. Once permit is acquired, the task is submitted to the underlying executor. Inside the submitted task, after the actual work is done, the semaphore permit is released. If the underlying executor rejects the task, maybe because it has been shut down, we release the permit immediately to avoid leaking it. And then we throw that exception. So how to use it? So here I have a thread pool executor where core pool size and max pool size is set to 3. Keep alive time is 0 seconds and the worker queue is a bounded queue with capacity of 2. We use this executor and the bound, which is summation of pool size and queue capacity, and pass it to our bounded executor. Then we submit 10 tasks to this bounded executor one by one. Each task log the task ID, then sleep for 2 seconds. If it gets interrupted, we restore its status and then it's finished. And once all tasks are finished, we shut down the executor gracefully with the timeout of 30 seconds. The key benefits of this bounded executor is this provides natural back pressure. When the system is overloaded, new tasks are not dropped or thrown as exceptions. Instead, the caller, example a web server thread, blocks, naturally slowing down the request rate and allowing the system to recover. This is much more graceful degradation than throwing rejected execution exception. So let me run this. So we are submitting 10 tasks. Submit a task, submitted successfully, second, third, fourth, fifth, sixth. Oops, we got the rejected execution exception. But wait, we didn't shut down the executor. Then how come we got rejected exception? The program is not stopped yet. So let's debug. Let me stop this and create a debug pointer and run it in a debug mode. We got it. So the executor threw the rejected execution exception while submitting the task. If we check the logs, so we submitted first, second, third, fourth, and fifth task, and while submitting the sixth task, we got that error. So this is strange. We submitted the task 6. All 5 permits are acquired. How come 6th task got the permit? And if it got the permit, why did executor reject the 6th task if it has the permit? So here is the reason. When we submit tasks sequentially, the way we are doing here, the first 5 acquire permits and go through. On the 6th submission, we expect this acquire call to block. But in practice, one of the earlier tasks may finish quickly and release its permit. That allows the 6th task to acquire the permit, but the executor is still saturated. 3 threads are busy and 2 tasks are queued. Queue is full and all threads are busy. So executor.execute method throws rejected execution exception. This mismatch happens because Semaphore tracks permits, which is external bound, but the executor tracks threads plus queue slots, which is internal bound. they are not perfectly synchronized. So a permit can be released while the queue is still full. So how to fix it? Instead of using bounded queue, we can switch to an unbounded linked blocking queue. That way, the executor never rejects the task. But to prevent runaway memory usage, we keep the semaphore as the true throttle. So the pattern becomes executor with unbounded queue, so there are no rejections, and semaphore with fixed permits. That's our chosen bound depending upon the requirements. This ensures no rejected execution exceptions when we submit the task and no unbounded memory growth, because at most the count of tasks in queue will never be more than number of permits. So let's rerun it by changing worker queue to unbounded link blocking queue, and let's observe the queue size even when we submit, let's say, 100 tasks. Also, let me set the pool size equal to the available CPU cores. So here you can see we have successfully completed the execution and the shutdown. So here we have pool size of 16. That means we have 16 threads, and bound is 18. That means at max 18 tasks will be in pending state, either in running or queued. Since our bound or queue capacity is 2. So if we check the queue size, so here I see 1. If I go down, so I see at max 4, 5. Here I can see. So you noticed here the queue size is not more than the bound, which is 18. So will not get memory issues. And that's how you create a bounded executor which blocks the submitter thread and creates a natural back pressure. If you found this video helpful, please give it a thumbs up and subscribe for more technical content.